Let's just jump right in. If you've used any modern AI chatbot lately, you've probably felt that weird mix of awe and, honestly, maybe a tiny bit of unease, right? It just sounds so incredibly human. Well, in this explainer, we're going to pull back the curtain on large language models. We're going to see exactly how these things transform from, magical talking boxes into highly structured, totally understandable computational engines.
We have a lot of really fascinating ground to cover today. We're going to break this down into 6 parts: the magic of conversation, next word prediction engines, the 3 stages of training, controlling the generation, grading the AI, and finally, ethical and safety risks.
All right, part 1, the magic of conversation.
Humanity has basically always been obsessed with the idea of inanimate objects talking back to us. Agatha Christie actually hit the nail on the head in her book, The Moving Finger, when she wrote, "How much do we know at any time? Much more, or so I believe, than we know we know." It's a brilliant quote because it perfectly captures this deep-seated desire we have to explore sentience and knowledge through conversation. We literally learn about ourselves and our world by talking. It's a theme you see everywhere, spanning from ancient mythology right up to modern literature.
Seriously, you can trace this obsession right through history. We go all the way back to antiquity with Ovid's myth of Pygmalion statue coming to life. Fast forward to 1818 with Mary Shelley's Frankenstein, and then, boom, 1966, we get Eliza. Eliza was this early computational chatbot designed to simulate a psychologist. And the wild thing is, its creator found that people were getting deeply emotionally attached to this machine. They were sharing their most intimate secrets with what was essentially just basic code. It perfectly sets the stage for the modern models we use today because it proves we are just hardwired to connect with absolutely anything that talks back to us.
Moving on to part 2, next word prediction engines. It is definitely time to shatter the illusion of magic here and reveal the core trick behind the wizard's curtain.
The absolute crucial thing to understand is that these models do not actually know facts. They don't have thoughts, they don't have feelings, and they aren't scanning some mental encyclopedia. They are what we call autoregressive language models. In plain English, they are computational systems that iteratively predict and generate words left to right based purely on probability distributions. Honestly, think of them like an autocorrect on absolute steroids. They read a sequence of words, guess the next token, and repeat. That's the whole shebang. Let's look at a super concrete example. Say we give the model this simple prefix. The square root of 4 is blank. Now, it doesn't whip out a calculator to do the math. Instead, it uses all that rich contextual processing it learned from reading a massive amount of text, and it just fills in the blank with a 2. Why? Because it has seen similar sentence structures enough times to know, statistically, what word usually comes next. And here is the actual math happening under the hood. Let's say it's predicting the next word for something like "so long and thanks for." The machine generates these raw scores called logits for literally every single word in its entire vocabulary. Then a mathematical function called a softmax swoops in and converts those raw logit scores into strict percentage probabilities. So in this case, the word all gets a 44% chance, making it the most likely next word. It is pure, beautiful statistical probability at work.
Which brings us to part 3, the 3 stages of training. Let's see how these models actually get so incredibly smart. The training happens in 3 distinct phases. First up is pre-training, which is where the model learns the basic mechanics of language by just guessing the next word across billions of documents. Next is instruction tuning. This is where we actually teach it to follow specific commands and answer questions so it doesn't just ramble on forever. And finally, alignment. This is where the model is trained, usually by human preference, to prioritize being helpful while learning to be less harmful or dangerous. Just to put that massive first step, pre-training, into perspective, these models devour data on a scale that's hard to even wrap your head around. Take a training corpus like the Pile, for example. It's an 800 gigabyte dataset. It's this enormous Frankenstein's monster of web text, Wikipedia articles, digitized books, dense academic papers from PubMed and Archive, dialogue from subtitles, and even raw code from GitHub. All of it scraped right off the internet. The AI reads it all, masking words and guessing them over and over until its internal probabilities map perfectly to human language.
All right, section 4, controlling the generation. So once the model is fully trained, we run into a new challenge. How do we actually dictate the way it generates text from those probabilities we just talked about? Well, think of this control mechanism exactly like a thermostat. On one hand, you have greedy decoding. This means the model always chooses the absolute most likely token. It's safe, sure, but it leads to highly predictable, generic, and honestly very boring text. But then you have temperature sampling. You can literally crank up the temperature parameter to reshape those probabilities. It introduces a bit of dynamic chaos and creativity into the generation. Suddenly, the model might pick slightly less probable words, which makes the text feel incredibly dynamic, human, and natural.
Now, we also control generation from our end through prompting. You have system prompts, which set the overall rules, like telling the AI, hey, your role is to be a helpful assistant. Then you have zero-shot prompting, where you just give it an instruction with 0 examples. But here's the real game changer, few-shot prompting. If you include just a few labeled examples or demonstrations in your prompt, you can massively improve the system's accuracy. The model figures out the format and logic you want right on the fly. We call this in-context learning because it improves task performance via the prompt without us having to go in and change any of the model's underlying code or weights.
On to Section 5, grading the AI. Because these models are just statistical engines and not, humans sitting down with a pencil taking a test, we need highly specific ways to grade their performance. One core metric computer scientists use is called perplexity. Basically, perplexity is a length-normalized metric that measures the inverse probability a model assigns to an unseen test set. I know, that is a mouthful. In plain terms, it measures how surprised the model is by real-world text. A lower perplexity score indicates a better language model because it means the model wasn't surprised. It's a highly accurate predictor of upcoming words.
But obviously, just predicting words isn't enough for us. We want to test actual reasoning and world knowledge. To do that, researchers use massive benchmarks, like the MMLU. The MMLU consists of exactly 15,908 multiple-choice knowledge questions, and they are not easy. They span 57 distinct subjects, covering everything from high school math to professional-level law and medicine.
But there is a massive catch here that we have to watch out for. What happens if the AI accidentally studies the test? We call this data contamination. Because these models are trained by scraping basically the entire internet, we constantly have to worry that the model inadvertently memorized the test set during its pre-training phase. If it already saw those exact MMLU questions hidden deep in its training data, its high score isn't actually true reasoning. It's just regurgitation.
Finally, Section 6, ethical and safety risks. Understanding that this AI is really just a statistical engine predicting words brings us to the very real-world dangers of deploying this technology at scale. There are major ethical and safety risks. Because it only knows statistical distributions, it doesn't actually know truth from fiction. That makes it incredibly prone to hallucinations, meaning it will generate completely false information with absolute confidence. Then there's sycophancy, where it'll flatter you and excessively agree with you even if you're dead wrong, which is obviously terrible if you're asking for educational or medical advice. It can also generate toxic bias, pushing abusive stereotypes or discriminating against certain dialects based on the darkest corners of the web it read. And of course, privacy leaks, where it might just spit out personal data, like phone numbers that were accidentally scooped up in its training sets.
So, knowing what you now know about the literal math happening behind the curtain, I want to leave you with this thought. We started by talking about ELIZA and humanity's obsession with talking to objects. Is the real danger here actually the machine's code? Or is it our fundamental hardwired human tendency to anthropomorphize these machines? When we blindly trust a math equation as if it were a living, breathing human expert, we expose ourselves to all of those risks. Food for thought. Thanks for hanging out with me for this explainer, and remember to keep questioning the magic.